assuming there was a VGA cable here momentarily. There isn't. Okay, so yeah, welcome. Thank you very much, Dave, for the great introductions. I don't need to talk anything, or I don't need to mention anything about the actual Graph500, so I'll just focus on the green Graph500. I also want to acknowledge the whole Graph500 executive committee, which has been very helpful in this process of putting this list together. So we are tightly synchronized, and this is actually a very important part of my work. So essentially, what we are trying to do with the green Graph500 thingy is to understand what really influences the power consumption and maybe set a different optimization goal. So there's performance, obviously, is an optimization goal, but there may also be power. And especially in data-driven applications like graph computations, like we hear in the exascale discussions, that data movement is most likely going to be the most expensive operation on the machine. So there may actually be techniques that will trade off performance for power, especially in this area of big data computing, or whatever we want to call it here. So in the context of the Graph500. So the idea is really to collaborate as closely as possible with the Graph500 that has been working greatly. However, we will have separate lists and separate awards because, as I said, those are different optimization goals. And we will see that the entries from the Graph500 and green Graph500 differ quite a bit in several senses. So, and what we also try to do is we try to stay compatible with the green 500 list, which means that as with the Graph500 and the top 500, we will be able to compare between those lists later. So we can then really say, like David just showed what the number 1 and number 5 is. I won't go that far in this talk. It's just the first list, so we have to catch up a little bit with the Graph500 list since they're already at number 6. But we will do cross-analyses later, and one thing that we will also do, we will do real measurements only. So all systems that are included in this list will have real measurements running the real code. So this is no TDP or anything that may have been that you may think. So just get right into the received submissions. So this is just a scatter plot of the submissions that they received this year. There were about a little bit more than 20. And so what the x-axis is the graph scale, pretty much like David has shown in his plot. But there it was gigabytes per gigabytes, but it's really the same scale. And then we have the energy mapping here, which we measure in megataps per watt. So it's not giga, so it's megataps per watt because it's not that power efficient. And we basically received multiple entries that fall in the small graph category, as we can see over here, but have a really high efficiency, especially this one. So this one is a Tegra CPU, to just give it out. So you can essentially, like, we received submissions where people were essentially running the Graph500 benchmark on your cell phone. And of course, that'll beat anything, right, this thing up here. And there are a couple of more submissions. And then we have the really big submissions up to the scale 40, as we've seen. So we received a very wide spectrum of submissions. And they essentially fall into 2 classes. So if you look at this list, they fall into the single node case. So all of those submissions here are actually single node submissions. So there may be multi-core, they may have more than one core, as I said, but they're still within the same shared memory domain. Right? And then there are large submissions, and they're very small and typically very efficient. Right? As you can imagine, my cell phone can really compute a very small graph very fast, and if it has only 2 vertices, right? So this is essentially allowed. So the reason for this is that the Graph500 list does not have 500 entries yet, so I can essentially submit something that has like 2 vertices, right? And to deal with this, we have the following observation. So we have, based on this observation, we see that those fall into 2 categories, right? And to deal with this, well, as you can see, small data versus big data is really very, very fundamentally different from the efficiency perspective, right? We've just seen our submissions, and now the question is, how can we deal with this? And so the idea is that one first characterization that we could do is we could say single node versus multiple node. But then we get into this discussion, well, is it actually single node, or is it just in cache versus in memory? Because the single node you can always beat by having a complete problem size in level 1 cache, right? And then you can actually even beat that if you have a complete problem size in registers, like a GPU or something, right? So it's something that's really hard to decide where to draw the line between big and small submissions. So what we actually did, and we did a little bit of statistics here, so we looked at the submissions to the Graph500, so this figure down here is the Graph500 this year. We looked at the distribution of graph scale in those submissions. So what we found is that this is just sorted here. So this is the graph scale in the small diagram, which you probably can't see, just believe me. and this is the submission number and sorted by the graph scale, and this red line is the median. Here is exactly the same data, so this is just a histogram, the same thing here, graph scale, median here. We see that the median is about 31. So the median scale, if you sort all of the entries, submissions to the Graph500 by scale, and the median will be 31. And so what we then decided is essentially, this is how we draw the line. The median of the top of the green Graph500 submissions will essentially be our line to distinguish between small and large ones, which fits very well here because the median is here. So that works perfectly this time. So I'm very curious how it works next time. This is something that needs to be discovered. And so coming to the actual lists, so we have the small data list, and I don't want to go through every single detail, but we can see that this is actually, the lists are dominated by Japanese universities, which submitted all kinds of grade systems. So this is actually great because this is the Tegra here, right? And then we have a MacBook or a Mac Mini, and then a couple of special systems here, and another special system here. So this is perfect data. Thank you very much. And we can actually see if you keep the megatabs per watt in mind, right? So this is scale 20. So those are all below the median. So those are all below scale 31, and they have rather unimpressive gigatabs numbers, obviously, because they're like rather small systems, right? So in the Graph500 they would be rather low. However, they have this incredible efficiency, and keep this number in mind, 64. Because now we will actually go to the big data list where we have less submissions, because obviously it's harder to really measure power consumption of a full-scale system, so there's a large entry barrier here. And this list is dominated again by IBM, of course, because they're so high in the Graph500. And so, but there we see it's a factor of, it's an order of magnitude less efficiency for those systems. And this is something we need to work on, because we see the upper bound for the smaller systems essentially.
Of course, it has a supporting interconnect. So
yes, I know. This is something we need. This is still something we have to work on. And yes, of course, that is a gigantic system.
At the scale you have it, you'll work on it naturally. The level of memory will get larger, and then you'll just have no interconnect.
But then wait. Well, one thing will also move. One second, because the median will also move up. Right? So keep this in mind. As the submissions of the Graph500 grow, the median will move up in differentiation between small and large. Yes, it's always depending on the median. Because in the green 500 list, if you think about it, an entry can only be in the green 500 list if it is in the top 500 list. And there's a pretty high entry barrier, so I can't submit my in-cache level 1 lin-pack number because I will never make the top 500 list. Yes, there's a question.
What I didn't understand is, are these power consumption, are they measured under the benchmark, or that's a nominal power consumption?
Okay. So let me restate this, and yes, it's a very good question. So the power consumptions are actually measured while the benchmark is running. The benchmark has to be modified to report this power consumption, because what the benchmark is essentially doing, it runs a loop over 64 iterations with run the BFS, check the result, run the BFS, check the result. This is not what we want to measure. So we changed the benchmark slightly to just run the BFS iteratively without the checking, right, for a user-defined amount of time, which you can adjust to the accuracy of your power meter, essentially. So you can run the BFS for 30 minutes if you can only sample every 10 minutes. So this is a change document. You can download it of the webpage green.graph500.org. And this is otherwise totally equivalent to the Graph500 benchmark. It's really just changing the outer loop. And all those numbers that are reported here are actually really measured during the execution time. So this is one precondition for being on this list. Yes?
Interesting would be, we assume that all these machines might be the base model, but not also have lin-pack results. But it would be interesting to correlate the power consumption of the lin-pack benchmark to the power consumption of the green 500.
Yes, that data I don't have, but it's easy to do yourself. You can essentially go to the green 500 list and cross-correlate this data. This is part of the scientific goal of this list, because we want to understand how those power consumptions behave, if we want to tune them, how we want to tune them. And the first result I found pretty interesting. We give the students to read it too. Yes?
Were you there when we made the decision to allow any scale entry? Do you remember the reason why it ended up that way?
No.
Okay, so the reason why we allow any scale entry is actually not to pad the list. principally two things that happened. One was we actually had a minimum problem size. It was called small. If you look into the spec, you'll see small. And when we were building the first set of lists, we got a bunch of people who responded who said, I really want to submit to the list, but I can't do small. So we did tiny. And then we got emails that said, I really want to submit to the list, but I can't do tiny. So we did toy. And after that, we decided that we were just going to allow any problem size. And this was kind of philosophically Mark Sneer, I think, who was pushing this approach because it's a problem that solves itself, right? So by people who are really seeking to be at the top end of the list, like the administrator did, for example, you push the top end of the list up and people become more competitive. And the second thing is it gives us actually quite a lot of information about how the problem scales from a cell phone to a Blue Jeep.
Exactly.
Right?
And I totally agree. This is a great thing.
So it's funny, but it's not silly, I guess.
Oh wait, did I say it's silly?
No.
Okay, good. Because I don't think it's silly, because as Richard says, it solves itself. And this, essentially, we need this differentiation between small and big data only at the beginning, because later in the process, we may actually discard this whole differentiation. But right now, it would look rather strange to people, because it's obvious, as Rich pointed out, as soon as you have a network, your energy consumption will go up. Like, you have to support your network somehow, and this is why we differentiate. And we didn't want to randomly differentiate with like network or not, because then you can get into discussions, what is the network, is it a Luma network, or is it a shared memory domain? So we just pick the scale, which makes a lot of sense, at least for the data that we're seeing right now.
It's actually kind of an interesting statistic in terms of energy. It costs you about an order of magnitude more to get to memory than it does to compute. And it costs you about an order of magnitude more than that to go across the network. So you're actually getting exactly the
What
right
you're expecting.
result.
Yes. So there's a question right there.
I think it's very interesting to see that last spread in the sense that you see some chances for future architectures to come down to that kind of optimistic parameter given by the statements.
Yes, exactly. So again, this is the first list. This is very sparse. I do actually have the first 10 for both lists, first 10 certificates printed out. I don't want to present them here because I didn't talk to the winners before, but if you want to pick up your certificate, just come to me after the session. I will have the first ones printed. Okay, so I mean, this was essentially the list. And then to the future, again, the same thing as with the Graph500. So